Hi, I'm Rachael Livermore in Melbourne, Australia, and I'm with Jeffrey Silverman in San Francisco, California.
Today, our guest is Moiya McTier, who is a PhD student at Columbia University. Hey, Moiya, thanks for joining us.
Hey, thanks for having me.
So, what we're talking about today is a project that you've done, which I have to say I had no idea was a thing, looking for mountains on extrasolar planets. Could you tell us how that's a thing?
Well, I kind of made it a thing, or my advisor thought of the thing, and then I made it real. So, extrasolar planets, planets outside of our solar system, should, in theory, have just as many mountains as Earth if they're rocky, and a lot of them should be rocky. And using the methods that we already use to find those planets, we can actually determine if they have mountains on them.
So, how do you do that?
Uh, yeah, so just a little background. To find exoplanets, there are a couple of different methods we can use, but one of the most popular ones is transit photometry. And that depends on seeing a planet pass between us and a star. So if a planet passes in front of a star from our point of view, then it blocks some of the star's light. And we see something called a transit light curve, or like a little dip in the light, and we can study that to study the physical characteristics or to learn the physical characteristics of a planet.
So, when you're looking for mountains, are you looking for like deviations from being perfectly round?
Exactly. Yeah, so if you imagine a totally spherical planet passing in front of a star, then you're going to have a really boring looking light curve. That the dip that the planet creates is going to have a really flat bottom. But if a planet has mountains on it, then those mountains will show up in the silhouette that we see, that basically the planet's shadow that it casts on the star. And as the planet rotates, those the silhouette will change, and that will create jaggedness in the bottom of the transit light curve, what we call scatter in the transit bottom.
So, how big do these mountains have to be for you to detect it with our current technology? I looked up some numbers before chatting with you today, and the biggest mountain on Earth, Mount Everest, is only 0.1% of Earth's radius. If you look at Olympus Mons on Mars, that's about 0.7% of Mars's radius. So those are pretty big mountains compared to the planet, and still a tiny fraction of the size of the planet.
Exactly. Yeah, this is kind of the catch. I may have misled you a little bit. We can't actually do this now. Um, so I've had some trouble publishing the results of my research because a lot of people are kind of stuck on the fact that it's not feasible with current technology. And this was actually a huge part of my project. I spent months trying to figure out how feasible this is and what kind of technology we would need to find mountains. And with our best guess, it would take something like the overwhelmingly large telescope or the extremely large telescope, which would be about 100 meters across, um,
Wow.
to detect mountains on an exoplanet. But these are ground-based telescopes, so if we had something in space, then maybe we could even take like 70 meters.
Oh, well, if we only need 70.
I mean, when we're talking about signals that are as small as mountains on a planet that's millions of light years away, then that's actually pretty incredible that we could do this at all. And so the numbers we came up with, and of course, this is based on a specific scenario. So imagine a planet like Mars orbiting a white dwarf star, so a star that's about 1% the size of our own sun, and we would be able to detect mountains on that planet using just 3 hours of time on the overwhelmingly large telescope, which is pretty awesome, I think.
Yeah, 3 hours is not too long. I mean, Rachel, how long do you observe objects usually?
Yeah, I've stared at single objects for 20 plus hours, so yeah, that's not bad at all.
It's 3 hours of observing time, which would take about a couple of years to actually get, because these transits are pretty infrequent and very short.
Gotcha. So what does, if at some point in the future we do, find some mountains on exoplanets, what does that tell us? What can we learn from that about the planet, or maybe how it formed, or are we just looking for something that kind of looks like Earth again or Mars?
Yeah, this is the most exciting part of the project, is figuring out what we could learn with mountains once we find them. And well, first, just finding mountains would be cool. It would kind of confirm that Earth isn't unique, which is what I guess I try to do every day at work, just prove that Earth isn't special. And but there are other things we could learn too. So mountains themselves don't mean that the planet is habitable, but mountains form from processes that are linked to habitability. So one of those things is the movement of tectonic plates. Large mountain ranges like the Himalayas form when tectonic plates move and collide. And the movement of tectonic plates makes other things that are important for habitability possible, like the cycle that kind of moves carbon dioxide and other noxious gases out of the atmosphere. Another thing that forms really large mountains is internal volcanism. So Olympus Mons on Mars was formed because Mars doesn't really have tectonic plate movement anymore, but it has internal volcanism. So lava is coming up out of the surface of Mars and building up in the same place over millions of years. And that means that it can create really large mountains. If we see really large mountains, that tells us there's internal volcanism, which could be a source of heat for a planet if that planet happens to be outside the habitable zone of its star. So if otherwise it would be too cold, then this internal volcanism could heat it up.
So earlier, Moiya was saying that you, your advisor had this idea and you sort of, ran with it and made it real. You had this like eureka aha moment, right?
Yeah, that's what I said, but that's definitely not how it happened in real life. Originally, this wasn't even supposed to be my project. My advisor suggested this as a 2-week distraction, and it ended up taking the whole year. But this is how science gets done, where you think something will happen really quickly, and then it takes up an entire year of your time. And this is actually something that I talk about in my own podcast that I host. It's called So You Think You Can Science, where I talk about, how science actually gets done and what scientists do in their everyday life. So, yeah, we're on iTunes if you want to check it out.
Yeah, we'll put a link down below the video.
Awesome. Thanks.
So this was really cool. Thanks so much for talking to us. It's always interesting to hear about these kind of weird, off-the-wall things that people are working on in science. So thanks very much for your time today.
Thanks for having me. Thanks for letting me talk about mountains.
Cheers.
Cheers.